There is a jellyfish in the ocean right now that will never die. Not a myth, not a legend, a real biological, scientifically documented creature that can grow old, reverse its own aging, and start life over again, completely, like pressing rewind on a DVD. And here you are, a human being, the smartest species on the planet, the only creature that ever built a rocket, wrote a symphony, or questioned its own existence. And you start going gray at 25. Your knees start hurting before you're 40. Your memory gets foggy. Your skin wrinkles. Your body slowly, quietly, starts falling apart. And there is nothing you can do to stop it. Why? Why does the most intelligent animal on Earth also happen to age so badly? Tonight, we're going to find out. Hey guys, welcome back. Tonight we're going somewhere a little different. Not into a royal palace, not through a war, not into the rise and fall of an empire. Tonight, we're going somewhere much more personal than that. We're going inside the human body, inside the very cells and biology that make you you. And we're going to ask one of the most quietly devastating questions that almost nobody actually sits down and thinks about. Why do humans age? Not just that we age, but why we age so fast, why we age at all. And more importantly, why, when you compare us to some of the other creatures sharing this planet with us, we seem to have gotten one of the worst deals in the entire animal kingdom when it comes to human aging and lifespan. Because here's the thing, most people think aging is just normal, universal, inevitable, like gravity, like the sun rising in the east. They assume every living thing gets old and dies, and that's just the natural order of things. But that's actually not true. Aging, the kind of aging we experience, where the body deteriorates, where things start breaking down, where cells stop repairing themselves properly. That is not a universal law of nature. It is, in the most uncomfortable way possible, a choice that evolution made on our behalf, a trade-off, a deal that was struck billions of years ago, long before any of us had any say in the matter. And when you start to understand why that deal was made, and what it actually cost us, and how some animals managed to get a completely 100% free trial, different deal altogether, well, it changes how you think about being alive. So let's start at the very beginning. And I mean the very, very beginning. The body as a machine, and why machines break down. Okay, so here's a gentle way to start understanding biological aging in humans. Think of your body like a car. Not a fancy car, just a regular car. It works when it's new. It runs smoothly. Everything functions the way it's supposed to. But over time, with use, with weather, with the general brutality of existing in the physical world, parts start to wear out. The tires go. The engine gets tired. The paint fades. Things stop fitting together as perfectly as they once did. Now, a car doesn't care about this. It doesn't have feelings about rusting. But your body does something the car doesn't. Your body actually repairs itself. Constantly. Every single day your cells are doing maintenance, patching up damage, replacing worn-out parts. It's remarkable, actually. The human cell repair system is one of the most sophisticated things in nature. But here's the catch. It doesn't repair itself perfectly. Every time a cell divides, every time it makes it a copy of itself, there are tiny little errors, tiny little imperfections, like photocopying a document 1,000 times. The first copy is pretty good. The second copy is fine. But by the 1,000th copy, things have gotten a little blurry, a little off. Details get lost. Mistakes accumulate. And those accumulated mistakes, that's essentially what aging at the cellular level is. It's the slow, quiet, relentless buildup of biological errors over time. Scientists have a word for this process. They call it senescence, cellular senescence. And it's the reason why a 90-year-old human looks and feels so different from a 20-year-old human. The cells in that 90-year-old body have been copied and repaired and patched and divided so many times that the errors have stacked up to a level the body can no longer fully compensate for. Now, here's where it gets interesting, because some animals don't seem to have this problem, or at least, they have it much, much less severely than we do. And that raises the obvious question: why? The great inequality of aging. Let me give you some numbers, just to put this in perspective. A Greenland shark, a large, slow-moving shark that lives in the frigid waters of the North Atlantic, can live for over 500 years. 500 years. Scientists have found individual Greenland sharks that were swimming around in the 1500s, when Shakespeare was alive, when Columbus had just reached the Americas. That shark was already there, slowly gliding through the dark water, unbothered. A bowhead whale can live for over 200 years. There are bowhead whales alive today that were already old when Abraham Lincoln was president. The Aldabra giant tortoise, a gentle, lumbering creature that lives on islands in the Indian Ocean, routinely reaches 150 years of age. There was a famous tortoise named Jonathan, who was born around 1832 and was still alive well into the 21st century. He lived through world wars. He outlived every human who was alive when he was born. Twice over. The naked mole rat, which, to be completely honest, looks like a tiny, wrinkled, nearly blind little nightmare, barely ages at all in any meaningful biological sense. Its risk of dying doesn't increase as it gets older, the way ours does. A 30-year-old naked mole rat is, biologically speaking, almost as healthy as a 1-year-old naked mole rat. That is genuinely insane by the standards of how aging is supposed to work. And then there's the jellyfish I mentioned at the very beginning, Turritopsis dohrnii, the so-called immortal jellyfish, which can, when faced with stress or physical damage or old age, revert its cells entirely back to an earlier developmental state and start its life cycle over from scratch. It is, for all practical purposes, biologically immortal, at least in terms of aging. Now compare that to us. Average human life expectancy globally is somewhere around 70 to 75 years, depending on where you live and when you were born. In the developed world, with modern medicine, maybe 80 to 85 if you're lucky, and take care of yourself. The absolute oldest reliably documented human being in recorded history is a woman named Jeanne Calment, who lived to be 122 years old. Was a French woman named Jeanne Calment, who died in 1997 at the age of 122. 122 years. That's our maximum. That's the ceiling. That's as good as it gets. And by the time most humans reach that ceiling, if they somehow manage to get there, their bodies are in a state of profound deterioration. Their organs are struggling, their bones are fragile, their minds may have drifted. They exist at the absolute outer limit of what human longevity can sustain. Meanwhile, somewhere in the dark ocean, a 500-year-old Greenland shark is out there, doing absolutely fine, completely unbothered, wondering what all the fuss is about. So why did this happen to us? This is the question that scientists, philosophers, biologists, and frankly just regular people have been asking for thousands of years. Why do humans, who are by any measure the most cognitively advanced species on this planet, age so poorly compared to creatures that can't even write a grocery list? And the answer, when you start to piece it together, is both fascinating and slightly maddening, because it turns out that human aging isn't a mistake. It isn't a flaw in the design. It isn't something that went wrong. It is, in a very real and very strange sense, exactly what evolution intended. But to understand why evolution intended it, we have to go back a long, long way. We have to go back to a time before humans existed, before civilization, before fire and tools and language. We have to go back to the earliest days of our ancestors, the hominids who walked the African savanna somewhere between 2 and 4 million years ago. And we have to think about what their lives looked like, because evolution doesn't care about you living a long and fulfilling life. Evolution doesn't care about your knees hurting when you climb stairs. Evolution doesn't care that your eyesight starts going at 45, or that your hair turns gray, or that your body slowly betrays you over the course of decades. Evolution cares about one thing only: reproduction, passing on your genes, making the next generation. Everything else is secondary. Everything else is, from evolution's cold and indifferent perspective, irrelevant. And this one simple fact explains almost everything about why human aging works the way it does. The evolutionary bargain. Here's a list of the most popular and trending hashtags on Twitter: the deal. In the ancient environment where our ancestors lived, out on the open savanna, without antibiotics, without hospitals, without even basic shelter most of the time. The average early human was not surviving for very long anyway. We're not talking about people living to 80 and 90 then worrying about aging. We're talking about a world where you could be killed by a predator, by starvation, by infection, by injury, by childbirth, by 100 things that modern medicine has since rendered manageable or survivable. In that environment, living past the age of reproductive maturity, past the age where you'd already had your children and raised them to a point where they could fend for themselves, didn't offer much evolutionary advantage. You were already done with the most important biological task. So evolution, in its characteristic way of making trade-offs, essentially decided, why invest enormous amounts of biological energy into maintaining the body in perfect condition for 100 years, when that body almost certainly won't even survive past 40 anyway? Better to take that energy and redirect it into reproduction, into making more offspring earlier, into growing and maturing faster, into putting all your biological chips on the table early in life, when they actually have a chance of paying off, rather than saving them for a long and healthy old age that, in the ancient world, you were extremely unlikely to ever reach. This theory, and it's one of the most well-supported ideas in evolutionary biology and aging, is called the disposable soma theory. It was developed by a British biologist named Thomas Kirkwood in the 1970s, and the basic idea is exactly what it sounds like. The soma is your body, your physical self, and according to this theory, your body is, from evolution's perspective, disposable. It's a vehicle for your genes. It gets you to reproductive age. It helps you reproduce. It maybe sticks around long enough to help raise the offspring. And then, as far as natural selection is concerned, it can start to deteriorate. Its work is done. The resources that could have been spent on the project were not available on indefinite body maintenance, instead got redirected to reproduction. And so we age. We fall apart. We deteriorate, because in the brutal arithmetic of natural selection, that was the more efficient strategy. It's not personal, it's not cruel, exactly. It's just the math of survival, over millions of years. So now that we've established that aging is essentially an evolutionary trade-off, a bargain made on our behalf without our consent, as most evolutionary bargains are, let's spend some time with the animals that seem to have gotten a completely different deal. Because there is something genuinely humbling about sitting down and looking at the full spectrum of aging across the animal kingdom. Once you start doing that, you realize that aging rates in animals vary so dramatically, so wildly, so illogically from our human perspective, that it starts to feel less like a natural law, and more like a setting that somebody forgot to standardize. like whoever was in charge of dialing up the aging speed for different species just had a very long day and decided to be completely inconsistent about it. Some creatures got the dial turned all the way down to almost zero, and some of them, us included, got it cranked up uncomfortably high. The naked mole rat, nature's strangest gift to science. Let's start with the naked mole rat, because if there is a single animal that has caused more sleepless nights among aging researchers, it's the naked mole rat than any other creature. It is this peculiar, wrinkled, faintly disturbing little mammal. The naked mole rat, Heterocephalus glaber, lives underground in East Africa, in Kenya, Ethiopia, Somalia. It forms large colonies, kind of like ants or bees, with a single queen who does all the reproducing and a large workforce of non-breeding workers. They are essentially blind, almost entirely hairless, cold-blooded, in the sense that they can't regulate their own body temperature independently, and they look, let's be honest about this, deeply unsettling. But here is what makes them remarkable. Naked mole rats don't follow Gompertz's law. Now, Gompertz's law is a mathematical rule discovered in the 1820s by a British mathematician named Benjamin Gompertz, and it describes something that applies to virtually every animal ever studied. The rule is simple. As an animal gets older, it becomes more difficult to find a suitable mate. Its risk of dying increases exponentially. For humans, this means that your chance of dying in any given year roughly doubles every 8 years after adulthood. When you're 30, your annual mortality risk is very low. When you're 60, it's noticeably higher. When you're 80, it's considerably higher still. The older you get, the faster the risk rises, exponentially. This is Gompertz's law. And until scientists started seriously studying naked mole rats, it was considered basically universal for all mammals. Naked mole rats don't follow it. A study published in 2018 found that after naked mole rats reach sexual maturity, they are the longest living rodent, living up to 35 years of maturity. Their risk of dying at any given age essentially doesn't increase at all. A 10-year-old naked mole rat has roughly the same daily mortality risk as a 1-year-old naked mole rat. This shouldn't be possible. This violates everything we thought we understood about mammalian aging. And these aren't small animals with long lifespans because of their size. Size is actually a decent predictor of longevity in mammals. Bigger animals tend to live longer, but the naked mole rat is tiny. It weighs maybe 30 to 40 grams. Based on its body size alone, it should live maybe 6 years, 7 at the most. Naked mole rats live for over 30 years. They almost never get cancer. They show very little oxidative stress, the kind of cellular damage from reactive oxygen that accumulates in aging cells. Their proteins stay stable for longer. Their DNA repair mechanisms seem unusually robust. They produce unusual amounts of a specific type of hyaluronic acid that may protect their cells from becoming cancerous. Scientists have found that even in very old naked mole rats, multiple biomarkers of aging remain remarkably similar to those of young ones. The naked mole rat, in short, seems to have found a biological strategy for aging that is fundamentally different from the one mammals are supposed to use. And scientists are desperately trying to figure out exactly what it is, because if they can understand it fully, it could have profound implications for anti-aging research in humans. The tortoise, living on geological time. Now let's drift from the strange underground world of the naked mole rat to something a little more tranquil. The tortoise. Giant tortoises are among the longest-lived vertebrates on Earth. The Aldabra giant tortoise, which lives on a small island in the Seychelles in the Indian Ocean, lives for over 100 years, routinely lives for over 150 years. Galapagos tortoises are similar. Jonathan the tortoise, who lives on the island of St. Helena in the South Atlantic and is the world's oldest known living land animal, was born around 1832. He is, as I write this, estimated to be somewhere around 190 years old. 190. He was born before the American Civil War, before the invention of the telephone, before the light bulb, before automobiles. He was already middle-aged by the time the Titanic sank. And what's particularly interesting about tortoises isn't just that they live a long time at time, it's how they age. Tortoises are one of the few vertebrate animals that show what scientists call negligible senescence, meaning their bodies show little to no functional decline as they get older. They don't get slower, they don't get weaker, their organs don't progressively fail. Old tortoises are essentially just as capable as young tortoises. Why? A big part of it comes down to metabolism. Tortoises have an extraordinarily slow metabolic rate. They move slowly, they eat slowly, they do everything slowly. And this slowness, it turns out, has a profound effect on how fast the cellular wear and tear of aging accumulates. There's a theory in biology of aging called the rate of living theory. The basic idea is that there's a roughly inverse relationship between metabolic rate and lifespan. The faster an animal burns through energy, the shorter it tends to live. Small animals with fast metabolisms tend to live shorter lives. Mice, shrews, small birds tend to live just a few years. Large animals or animals with slow metabolisms tend to live much longer. Tortoises have taken this to one extreme. They burn energy so slowly, they move through time so patiently, that their cellular machinery accumulates damage at a fraction of the rate that ours does. The Greenland shark, ancient beyond comprehension. But if tortoises stretch the imagination, the Greenland shark simply breaks it. The Greenland shark, Somniosus microcephalus, is a massive, slow-moving shark that lives in the cold, deep waters of the North Atlantic and Arctic Ocean. It can grow to nearly 7 meters in length. It swims at roughly 1 kilometer per hour, painfully slowly for a fish, let alone a shark. It's essentially a large, cold, indifferent presence in some of the most remote water on Earth, and it can live for over 500 years. This was discovered somewhat recently. A major study published in Science in 2016 used radiocarbon dating to estimate the ages of Greenland sharks by analyzing proteins in their eye lenses, which form in the womb and are never replaced. The proteins in those lenses lock in a chemical signature from the water the shark swam through when it was young. And by measuring that chemical signature against known patterns of radioactive carbon in the ocean, patterns that changed measurably due to nuclear testing in the 1950s, scientists were able to estimate how old each shark was. The oldest individual they found was estimated to be approximately 392 years old, with a potential range up to 512, born potentially in the 1500s. These are animals that were alive during the age of exploration. Some of them were alive before the founding of the United States. Some may have been swimming through the deep ocean since before Shakespeare was born. And here's the uncomfortable thing. These sharks don't reach sexual maturity until they're approximately 150 years old. So from their perspective, they're not even adults until the point in time when most humans have been dead for a century. The sheer scale of their lives, compared to the scale of their lives to ours, is almost impossible to fully process. The immortal jellyfish, reversing time itself. And then there is Turritopsis dorni, the immortal jellyfish, which, as I mentioned in the opening, is in a category entirely its own. Most jellyfish follow the standard life cycle. They start as a free-swimming larva, then settle down to a benthic life cycle. They start as larvae, develop into polyps, then into medusas. the free-swimming bell-shaped form you picture when you think of a jellyfish. They reproduce, they age, they die. Turritopsis dohrnii does all of that. And then, when it gets old or sick or stressed, it does something that no other multicellular organism does. The organism is known to do in the same way. It undergoes a process called transdifferentiation, where its cells literally revert to an earlier developmental state. The adult medusa transforms back into a juvenile polyp, and then it grows up again. And when it gets old again, it reverses again. It can theoretically do this indefinitely. This is not regeneration. It's not just regrowing a lost limb, which plenty of animals can do. This is the entire organism, every cell in its body, reversing its developmental clock, going from old to young, from mature to juvenile, from the biological equivalent of 80 years old to the biological equivalent of 0, and starting over. The implications of this are staggering. Scientists who study cellular reprogramming and biological immortality have been intensely interested in this jellyfish for years, because if we could understand the exact biochemical mechanism that allows this reversal, if we could identify which genes are switched on and off, which proteins are involved, which signals trigger the process, the implications for extending human life could be extraordinary. Of course, applying the biology of a jellyfish to a human being is about 17,000 times more complicated than it sounds. But the basic fact that a biological system can do this, that a living creature can reverse its own aging at the cellular level, is enormous. Because it proves that aging is not an absolute biological inevitability. It is a process that can, at least in principle, be undone. Why some animals got such a better deal. So what is it exactly that gives these animals their extraordinary lifespans? Is it just metabolism? Is it genetics? Is it something in the environment? The honest answer is, it's a combination of things, and scientists are still working through all of it. But there are some patterns that keep emerging. One is DNA repair efficiency. Longer-lived animals tend to have more robust systems for repairing DNA damage, the micro-level errors and breaks that accumulate in cells over time. The naked mole rat, the bowhead whale, the Greenland shark, all of them seem to have DNA repair mechanisms that are notably more efficient than those of shorter-lived species. Another is telomere length and stability. Telomeres are the protective caps at the ends of chromosomes, like the plastic tips at the end of shoelaces. Every time a cell divides, telomeres get a tiny bit shorter. When they get too short, the cell can no longer divide properly, and it enters senescence or dies. Telomere shortening is one of the most well-understood hallmarks of aging, and some long-lived animals, including certain species of turtles, seem to have mechanisms for maintaining or even lengthening their telomeres over time, which is part of why they age so slowly. A third factor is cancer resistance. One of the key risks of living a very long time biologically is that the longer you live, the more chances your DNA has to develop mutations that become cancerous. Longer-lived animals tend to have evolved extraordinary cancer suppression mechanisms. The naked mole rat's unusual hyaluronic acid production is one example. Elephants, which live about 60 to 70 years, which is quite long for their size, have multiple extra copies of a gene called TP53, which is one of the most important tumor-suppressing genes in biology. Having extra copies means extra protection against cancer. Every long-lived animal seems to have solved the aging puzzle in its own slightly different way, and each solution gives scientists another piece of the larger picture. We've spent some time in the cold science of aging, in the biology, in the evolution, in the neat clinical world of cells and genes and telomeres, and that's important. That's the foundation. But here's the thing. Humans have been aging for a very long time, and for most of that time, they had absolutely no idea why it was happening. No microscopes, no genetics, no molecular biology, no concept of cells or DNA or telomeres. What they had was observation, experience, and an almost limitless capacity for coming up with explanations. Some brilliant, some bizarre, some deeply strange, and a few that turn out to have been surprisingly close to the truth by accident. So let's take a step back from the science for 2020, a moment, and travel through human history to see how different civilizations, in different times and places, understood the mystery of why humans grow old and die. Because the history of how we've thought about aging is, in its own way, just as interesting as the biology of aging itself. Ancient Egypt, the body as sacred architecture. Let's start in ancient Egypt, because the Egyptians, if nothing else, were deeply, obsessively concerned with the human body, and with what happened to it over time. Ancient Egyptian medicine had a surprisingly sophisticated understanding of anatomy for its era. They performed surgeries, they set broken bones, they had specific treatments for specific ailments. The Edwin Smith Papyrus, one of the oldest surviving medical texts in human history, dating to around 1600 BCE, but believed to be copied from an even older source, describes surgical procedures with a level of clinical precision that is genuinely impressive. But when it came to aging and longevity, even the Egyptians hit a wall, because their fundamental model of the human body was spiritual as much as it was physical. For the Egyptians, health and the state of the body were intimately tied to the balance of spiritual forces. The concept of Ma'at, harmony, balance, the right order of things, governed not just moral behavior, but physical well-being. When the body began to deteriorate, when old age set in, it was understood in part as an imbalance, a gradual disruption of the divine order that kept the body functioning. They also had some very specific ideas about what aging actually was at the physical level. One dominant theory in ancient Egyptian medicine was that aging was caused by the gradual accumulation of a kind of waste product in the body, something like rot or decay that built up over time and couldn't be fully expelled. The word they sometimes used was wakedu, a kind of harmful residue or substance that accumulated in the body and caused disease and deterioration. And honestly, that's not entirely wrong. Not in the specific mechanism, obviously, but the general idea that aging is caused by the accumulation of damage over time, by the accumulation of something harmful that the body can't fully clear, maps onto modern ideas about cellular waste accumulation, oxidative damage, and the buildup of senescent cells in aging tissue in a way that feels almost uncanny. Of course, the Egyptians also had solutions for this problem. Many of their recommended treatments for age-related decline involved purging, laxatives, enemas, dietary interventions designed to clear the body of its accumulated wakedu. The logic was sound, even if the specific application was, let's call it, ambitious. Ancient Greece, the four humors and the problem of cold. From Egypt, let's move to ancient Greece, and to a framework for understanding the body that would dominate Western medical thinking for nearly 2,000 years. The theory of the four humors. Hippocrates, the famous Greek physician whose name is attached to the Hippocratic Oath that doctors still reference today, developed, along with his students and contemporaries, a model of the human body based on four fundamental fluids: blood, phlegm, yellow bile, and black bile. Health was understood as the proper balance of these four fluids. Disease was an imbalance. Treatment was about restoring balance. And aging, in the Hippocratic framework, was understood primarily as a process of progressive drying and cooling. The idea was that life was fundamentally associated with heat and moisture. The young body was warm and moist. It had an abundant vital heat that sustained its functions. As time passed, this vital heat was gradually consumed. The body became drier, cooler, more dominated by cold, dry humors, particularly phlegm and black bile. And this progressive drying and cooling was what we experienced as old age. Aristotle elaborated on this framework in his work, The Nicomachean Ethics, his own writings. He wrote about aging as the exhaustion of the body's innate moisture, a concept he called the radical moisture, or innate humidity. Every living thing, Aristotle believed, had a finite supply of this fundamental life-sustaining moisture. Once it was used up, once the fire of life had finally consumed all available fuel, the body dried out completely. Death followed. It's a poetic framework. And again, it has some interesting parallels to modern understanding. The idea that the body gradually loses its capacity for maintenance and function over time, that there's a kind of fundamental resource that is progressively depleted. That's not entirely unlike modern ideas about cellular energy production declining with age, or the gradual loss of stem cell function, or the depletion of the body's repair capacity. But then, of course, the Hippocratic framework also recommended a lot of things that didn't work. Specific diets, particular herbs, careful management of environment, avoiding excessive cold, excessive heat, excessive dryness. The Greeks were deeply invested in the idea that you could slow aging through proper lifestyle management. And to their credit, they were right that lifestyle affects aging. They were just working with very incomplete information about how. Ancient China, qi, essence, and the infinite horizon of longevity. Meanwhile, on the other side of the world, ancient Chinese civilization was developing its own remarkably sophisticated understanding of aging. One that, in important ways, diverged fundamentally from the Greek model. Traditional Chinese medicine, which has its roots going back at least 3,000 years, understood the body through a system of vital energies and essences. The most fundamental of these was qi, sometimes spelled qi, the life force, or vital energy that animated all living things. But there was also jing, often translated as essence, a more fundamental and finite biological resource, somewhat analogous to what Aristotle called radical moisture, that was believed to be stored primarily in the kidneys and to be consumed over the course of a lifetime. Jing was understood as the biological capital of life. You were born with a finite supply of it, inherited from your parents. Everything you did that depleted your body, excessive sexual activity, overwork, stress, poor diet, consumed your jing faster. Everything you did that nourished your body, proper rest, good diet, meditation, specific herbs, regulated breathing, preserved and even supplemented your jing, the entire tradition of Taoist longevity practices, which became an elaborate and fascinating science. In ancient times, China was essentially a set of techniques for managing, preserving, and supplementing one's jing in order to extend life as long as possible. Ideally, forever. And I mean that literally. The Taoist longevity tradition included many figures who were believed to have achieved genuine physical immortality through the spiritual cultivation. The Xian, the Immortals, were humans who had so completely mastered the preservation and cultivation of their vital essence that they transcended the normal limitations of biological life. They were said to still be alive, somewhere in remote mountains or in hidden spiritual realms, having simply never run out of the vital substance that sustains life. Now, needless to say, nobody actually achieved biological immortality through Taoist practice, but the practices themselves were often remarkably sensible. The emphasis on moderate diet, stress reduction, regular gentle exercise, things like Tai Chi and Qigong, meditative breathing techniques, adequate sleep, the avoidance of excess in all things. These are all practices that modern longevity science would largely endorse as genuinely beneficial for healthy aging. The theoretical framework was wrong in the specifics. The Jing doesn't actually exist as a physical substance. Qi is not something that can be measured or quantified in the laboratory. But the behavioral recommendations that grew out of this framework have aged, ironically, far better than the people following them. The fountain of youth, humanity's oldest obsession. Now let's talk about the dream, because before we get into what the ancient world thought about aging, we have to spend some time with what the ancient world wanted to do about aging. The desire to live longer, ideally, forever, is one of the oldest and most consistent impulses in human history. It shows up in virtually every culture, every civilization, every era, and it has produced some of the most extraordinary, deluded, poetic, and sometimes dangerous quests in the entire story of humanity. The Fountain of Youth is probably the most famous version of this dream. The idea of a magical spring or pool whose waters could restore youth or grant immortality appears in ancient Hindu texts. The Kanda Purana describes a pool whose waters can bring dead men back to life. It appears in ancient Greek mythology. In the stories of Alexander the Great, who according to legend was told of a water of life somewhere in the land of darkness, beyond the eastern edge of the known world. In the ancient Mesopotamian epic of Gilgamesh, one of the oldest written stories in human history, the hero Gilgamesh actually goes on a quest specifically to find the secret of immortality after watching his best friend die. The Epic of Gilgamesh is at least 4,000 years old, and its central emotional question, why do humans have to die? Why can't we live forever? Is there any way to escape aging? Is exactly the question that we are exploring in this video, tonight, thousands of years later. Nothing changes, does it? There's actually a famous video that a lot of history enthusiasts will have come across. A video called something like The History of Immortality that walks through these ancient quests for eternal life in a broad sweep. And if you've watched something like that before, you'll have some sense of just how universal and ancient this desire really is. But tonight, we're going to go deeper than a broad overview. We're going to look at some of the specific, strange, and sometimes darkly fascinating ways that particular civilizations attempted to actually achieve longer life. Not in legend, but in practice. Ancient Rome, wine, blood, and the Roman approach to old age. The Romans were, in many ways, a deeply practical civilization, and their approach to aging reflected that practicality, mixed, as Roman things often were, with a certain amount of excess and a willingness to try things that modern people would find alarming. Roman medicine built heavily on the Greek framework, the four humors, the vital heat, the importance of balance. But Roman physicians, particularly Galen, the enormously influential Greek-born thousands, Zhaos, thousands, Zhaos, physician who practiced in Rome in the 2nd century CE, and whose work would shape Western medicine for over 1,000 years, added layers of their own. Galen believed deeply in the importance of diet, exercise, bathing, and lifestyle management for healthy aging. His 6 non-naturals, the factors that were neither built into the body nor entirely outside of it, but that people could manage through their choices, included air quality, food and drink, sleep, exercise, emotional state, and the retention or evacuation of bodily substances. Managing all six properly, Galen believed, could substantially extend healthy life. And in many ways, he was right. Not completely right, not right in all the details, but right in the general principle that lifestyle factors have a profound effect on how we age. This is something that modern geroscience absolutely confirms. But the Romans also had some less rigorously supported approaches. There was, for instance, a Roman belief, shared by some other ancient cultures, that the blood of young people had particular rejuvenating properties, that being in physical contact with the young and vigorous, sharing meals with them, sleeping near them, breathing their air, could transfer some of that youthful vitality to an older person. This was called gerochemy, literally, the care of old men by young people. Some Roman physicians recommended that elderly men sleep with young women, not primarily for any erotic reason, but specifically to absorb their youthful warmth and energy. This was understood as a genuine medical treatment. King David, in the Old Testament, was described as being attended by a young woman named Abishag, the Shunammite, specifically for this purpose, to provide her warmth to the aging king. This practice was apparently common enough that it had a name. So far, we've drifted through the ancient world, through Egypt and Greece and Rome and China, and we've seen how people, without microscopes or genetics, tried to make sense of something that is still, even with all of our modern tools, not fully understood. And now things get a little more chaotic, because we're moving into the medieval period, and then into the Renaissance, and then into the early scientific age. And along the way, the quest to understand and defeat aging picks up some truly remarkable characters, including a few who would be considered either visionaries or complete frauds, depending on who you ask, sometimes both simultaneously. The medieval period, where aging meets alchemy. The medieval understanding of aging in Europe was essentially a slightly modified version of the Galenic framework, the four humors, the vital heat, the importance of lifestyle. The church added its own overlay, old age as a gift from God, a preparation for the afterlife, a natural process divinely ordained. This created an interesting tension, because on one hand, Christian theology taught that the body was a temporary vessel, and death, a passage, not an end, which somewhat reduced the urgency of fighting aging. But on the other hand, many people very much wanted to live longer, regardless of theological frameworks. And this is where alchemy comes in. Alchemy in the Middle Ages was a genuine intellectual and scientific tradition, not just a fantasy. Alchemists weren't simply deluded fools chasing magical gold. Many of them were serious scholars who combined elements of Greek philosophy, Arabic chemistry, and other elements of the Islamic world and spiritual thought into an attempt to understand the fundamental nature of matter and life. And one of their most significant goals, alongside transmuting base metals into gold, was the discovery of the Elixir of Life, a substance that could cure all disease, stop aging, and grant immortality. This wasn't a fairy tale to the medieval alchemist. It was a serious scientific project. The reasoning went something like this. If the universe was made of fundamental principles that could be isolated and purified, then the principle of life and vitality could, in theory, also be isolated and concentrated. The perfectly purified essence of life, the quintessence, the fifth element beyond earth, water, fire, and air, would, if it could be extracted and administered, restore and preserve life indefinitely. Roger Bacon, the 13th century English friar and philosopher, who is often credited as one of the earliest advocates of the empirical scientific method, wrote extensively about aging and longevity. He believed that human lifespan could be dramatically extended through proper knowledge. He studied the lives of ancient biblical figures, people like Methuselah, who Genesis says lived to 969 years, and concluded that early humans had possessed knowledge of how to preserve their vital moisture that had been lost over time. Bacon actually wrote a book on the subject, De Retardatione Accidentium Senectutis, on the retardation of the accidents of olden age. In it, he described specific regimens: careful diet, clean air, moderated activity, the use of particular substances including gold, aloe, and the meat of vipers, that he believed could substantially slow the aging process. The viper thing is interesting, actually. Snake meat was considered a genuine medicine for aging in multiple cultures across history. The reasoning varied. Sometimes it was about the snake's ability to shed its skin and renew itself. Sometimes it was about specific nutrients or properties attributed to snake meat. But it shows up repeatedly, in different cultures, without apparent contact between them, as a proposed remedy for age-related decline. Paracelsus, the wildest chemist in history. And then there is Paracelsus, Theophrastus Bombastus von Hohenheim, who is remembered by history under the name Paracelsus, was a 16th century Swiss-German physician, alchemist, and philosopher who was either a genius or a madman, or both, and who essentially tore up the Galenic framework and started over from scratch. Paracelsus rejected the four humors entirely. He believed that the body was fundamentally chemical in nature, not governed by spiritual forces or vital fluids, but by specific chemical processes that could be understood, interrupted, and potentially corrected through the right chemical interventions. This was revolutionary. This was, in a real sense, the beginning of the idea that chemistry and medicine are fundamentally one-linked, an idea that leads, in a direct intellectual line, to modern pharmacology. His ideas about aging were characteristically extreme. He believed that the body accumulated a kind of mineral calcification over time. Literally, that life processes produced a kind of internal tartar or stone, similar to what builds up on teeth, and that this accumulation was what caused aging and death. The solution naturally was chemical intervention, dissolving this accumulated deposit through appropriate treatments. He was wrong about the mechanism, obviously, but the general concept, that aging involves the accumulation of something harmful in the body that chemical intervention might address, is again not wildly different from some modern ideas about clearing senescent cells or reducing protein aggregation in aging tissue. Paracelsus also worked extensively with mercury, arsenic, and other substances that we now know to be profoundly toxic. His medical career was, to put it charitably, mixed in terms of outcomes. He cured some people and almost certainly killed others, but his legacy is enormous. He helped push European medicine from a primarily philosophical to a primarily scientific approach to tradition, towards something more empirical, more chemical, more interested in mechanism than in abstract theory. And he spent a considerable portion of his life looking for the elixir of life. He believed he was close. He probably wasn't. The 17th century. Francis Bacon and the first scientific approach to aging. The person who perhaps most clearly articulated the idea that aging was a scientific problem. Not a spiritual one, not a mystical one, but a problem that empirical investigation could eventually solve, was Francis Bacon. Francis Bacon, the English statesman, philosopher, and one of the founders of the modern scientific method, published a book in 1623 called Historia Vitae et Mortis, the history of life and death. It is one of the earliest systematic scientific investigations into the mechanisms of aging. Bacon approached aging the way he one Hansen Mylesent. approached every other natural phenomenon as something to be studied, observed, catalogued, and understood through careful empirical investigation. He was deeply interested in what factors contributed to long life and what factors shortened it. He analyzed the lifestyles of very old people. He looked at environmental factors. He examined diet and activity. He made careful observations about which peoples and regions seemed to produce longer-lived individuals. His conclusions were sometimes wrong. He was working with incomplete information and methods that were primitive by modern standards. But his approach was fundamentally right. The idea that aging is a natural process subject to scientific understanding, that it can be studied systematically, that the factors contributing to it can be identified and potentially modified. This is the foundation of modern geroscience and longevity research. Bacon explicitly argued that extending human life was one of the most important goals science could pursue. He believed that if enough careful observations were made and enough experiments conducted, the mechanisms of aging could be understood well enough to substantially slow the process. He didn't believe in magic potions or elixirs. He believed in data and method. He was right. He was just about 400 years early, the 19th century, when science started getting serious. The 19th century was when the scientific study of aging really began to take shape, and it did so through a combination of developments: the rise of modern chemistry, the development of cell theory, and eventually the revolution of evolutionary biology. That together began to give scientists genuinely powerful tools for understanding why living things age. The development of cell theory in the 1830s and 1840s, the discovery that all living things are made of cells, and that cells come from other cells, was fundamental. Because once you understood the cell as the basic unit of life, you could start asking questions about what happens to cells over time. Why do they stop working properly? Why do they stop dividing? Why do they die? Then came Darwin. Charles Darwin's theory of evolution by natural selection, published in 1859, provided the theoretical framework that eventually allowed scientists to ask the most important question about aging. Why does it exist at all? Why would natural selection produce creatures that deteriorate with time, rather than maintaining themselves indefinitely? We already touched on the answer: the disposable soma theory, the evolutionary trade-off between reproduction and longevity. But it took decades after Darwin for these ideas to be fully worked out. The theoretical framework for evolutionary theories of aging was primarily developed in the mid-20th century by scientists like Peter Medawar, George Williams, and Thomas Kirkwood. What the 19th century contributed, though, was the beginning of systematic biogerontology, the scientific study of biological aging. Scientists began to look carefully at aging cells, aging tissues, aging organisms. They began to develop the concept of biological age, distinct from chronological age. They began to notice that some animals age much faster than others. They began to ask the comparative questions that are still being asked today. The 20th century, from cells to genes to hallmarks, and then the 20th century happened, and everything accelerated. The discovery of the structure of DNA by Watson and Crick in 1953, building on the X-ray crystallography work of Rosalind Franklin, opened an entirely new dimension of aging research. Suddenly, it was possible to think about aging, not just in terms of cells or chemistry, but in terms of the fundamental information-carrying molecules of life, the genome, the instructions, and what scientists found as they began to study the genome in relation to aging was extraordinary. Genes that influence aging exist. Mutations in specific genes can dramatically extend or shorten lifespan in model organisms. A mutation in a single gene, the DAF2 gene, in a tiny roundworm called C. elegans, can double the worm's lifespan. A single gene, double the lifespan. This was a conceptual earthquake, because it meant that lifespan is not fixed. It is not an unalterable law of physics. It is a biological parameter, a dial that evolution has set at a particular value for reasons we can understand, using mechanisms we can study, and potentially mechanisms we can modify. The discovery of telomeres and telomerase by scientists Elizabeth Blackburn, Carol Greider, and Jack Szostak, who shared the Nobel Prize in Physiology or Medicine in 2009, added another crucial piece. Telomeres are the protective caps on chromosomes that shorten with age, each cell division. Telomerase is an enzyme that can rebuild them. Understanding how telomere shortening contributes to cellular aging opened up a whole new avenue of research. And in 2013, a landmark paper in the journal Cell by a group of leading aging researchers identified what they called the 9 hallmarks of aging, the fundamental biological processes that drive the deterioration of the body with time. These 9 hallmarks, including genomic instability, telomere attrition, epigenetic alterations, loss of proteostasis, deregulated nutrient sensing, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and altered intercellular communication, provided the field with a unifying framework. For the first time, scientists could look at aging not as a single process, but as a collection of distinct interrelated mechanisms, each of which could potentially be targeted separately. The era of precision geroscience had begun. We've come a long way. We started in the ancient world, with people who genuinely didn't know what was happening when the body aged, who built beautiful and sometimes surprisingly insightful frameworks for understanding it, and who dreamed enormous dreams about overcoming it. We moved through the medieval alchemists and their elixirs, through the scientific revolution and its growing empirical framework, through the 19th century and its foundational discoveries, and into the 20th century's molecular revolution. And now we're here, in the 21st century, where for the first time in the entire history of human civilization, the question is no longer why do we age, because we largely understand that, but rather, can we actually stop it? And the answer, quietly, carefully, cautiously, is that we might be getting close. The longevity industry, billions and billions of reasons. The modern anti-aging and longevity industry is, depending on how you measure it, somewhere between $100 billion and $1 trillion enterprise. The exact number depends on what you include. Are we talking just the high-end molecular biology research labs, or also the supplements, the skincare, the clinics, the dietary interventions? Are we including the tech billionaires who are pouring hundreds of millions of dollars into their own personal immortality projects? Because yes, that is a thing that is happening. Jeff Bezos has invested in a longevity biotech company called Altos Labs. Peter Thiel has been publicly vocal about his interest in living dramatically longer and has invested accordingly. Yuri Milner, the Russian-American tech investor, has backed multiple longevity initiatives. Larry Ellison, the co-founder of Oracle, has donated over $430 million to aging research over his career, reportedly motivated partly by his frank refusal to accept that he is going to die. Sam Altman, the CEO of a major AI company that you will probably have heard of, has invested in a startup called Retro Biosciences, with the stated goal of adding 10 years to the average human lifespan. These aren't fringe investments. These are major bets by some of the most commercially successful people in the world. And they are all, in various ways, betting that the science of aging has reached a point where genuine intervention, not just slowing aging slightly through lifestyle choices, but actually targeting its fundamental biological mechanisms, is becoming possible. Senolytics, clearing out the zombie cells. One of the most exciting areas of longevity research is the study of the effects of aging on the brain right now, is senolytics. And to understand why, you need to understand what senescent cells actually do in the aging body. We talked earlier about cellular senescence, the process where cells stop dividing and enter a kind of permanent, non-functional state. When cells first become senescent, this is actually a useful feature. Senescence is one of the body's defenses against cancer. It's a way of stopping damaged cells from continuing to divide uncontrollably. Senescent cells also play a role in wound healing. But here's the problem. Senescent cells don't just quietly stop working. They continue to exist in the tissue. They continue to consume resources. And, crucially, they release a cocktail of inflammatory chemical signals into the surrounding tissue that can damage neighboring healthy cells and contribute to a chronic state of low-grade inflammation in aging tissue. Scientists call this the SASP, the senescence-associated secretory phenotype, and it's one of the mechanisms that connects cellular aging to the broader tissue and organ deterioration we experience as old age. In young people, the immune system efficiently clears senescent cells, but as we age, the immune system becomes less effective at this task. Senescent cells accumulate. The inflammatory signals they release build up, and this contributes to the aging of essentially every tissue and organ in the body. Senolytics are drugs designed to selectively kill senescent cells, to clear them out of the body and reduce the inflammatory burden they create. The concept was first demonstrated in mice in 2011 by researchers at the Mayo Clinic, and the results were striking. When senescent cells were cleared from aging mice, the mice showed improvements in multiple aspects of aging: delayed onset of age-related conditions, improved physical function, and even, in some experiments, extended lifespan. The first human clinical trials for senolytic drugs are now underway. Dasatinib and quercetin, two drugs that seem to selectively trigger senescent cell death, have been tested in small human trials with some promising early results. It's early days. The science is not yet at the stage where a senolytic drug is going to be prescribed by your doctor, but the direction of the research is genuinely exciting. The idea that you could take a drug or follow a treatment protocol that specifically removes the accumulated zombie cells from your body, reduces inflammation, and restores some of the tissue function that aging has degraded. That's a real scientific project right now. It's not science fiction. Rapamycin, the accidental longevity drug. Then there's rapamycin, which has one of the more interesting origin stories in pharmacology. Rapamycin was discovered in the 1960s and 1970s from a bacterium found in soil samples taken from Easter Island. Rapa Nui in the native language, which is where the drug gets its name. It was originally developed as an antifungal compound, then as an immunosuppressant for organ transplant patients, because it suppresses the immune response that would otherwise cause transplant rejection. Nobody was thinking about aging or longevity when they were studying rapamycin. But then, in 2009, a landmark study showed that rapamycin extended the lifespan of mice, even when the drug was first administered, when the mice were already elderly, equivalent to about 60 years in human terms. This was remarkable. The drug extended lifespan by about 9 to 14% in those mice, and it did so through a specific molecular pathway, the mTOR pathway, which stands for Mechanistic Target of Rapamycin. The mTOR pathway is essentially a cellular sensor for nutrient availability. When nutrients are abundant, mTOR is active, and cells prioritize growth and reproduction. When nutrients are scarce, mTOR is suppressed, and cells shift into a more maintenance-focused mode, activating autophagy, the cellular self-cleaning process that breaks down and recycles damaged components. It turns out that persistently high mTOR activity, the default state in well-fed modern humans, may actually accelerate aging. By suppressing mTOR with rapamycin, you shift cells into that maintenance mode more of the time, giving the body more opportunity to clear damaged components and repair itself. The connection between mTOR, nutrient sensing, and aging has become one of the most actively researched areas in longevity biology, and rapamycin, despite its existing use as an immunosuppressant and the side effects that entails, is now being taken experimentally by some people interested in extending healthy lifespan, including, reportedly, a number of prominent figures in the tech industry. Caloric restriction, the one thing that works consistently. Here's an awkward fact about longevity science. For all the billions of dollars being invested, for all the brilliant researchers working on senolytics and rapamycin and gene therapy and stem cells, there is one intervention that has been shown, repeatedly, across dozens of different animal species, to reliably extend lifespan. And it's not a drug. It's not a cutting-edge biotechnology. It's not a gene edit. It's eating less. Caloric restriction. Reducing calorie intake by somewhere between 20 and 40%, while maintaining adequate nutrition. Has extended lifespan in every animal model it has been rigorously tested in, from yeast to worms to flies to mice, and in primates, rhesus monkeys. Long-term studies have shown that caloric restriction dramatically reduces the incidence of age-related diseases and appears to extend both health span and, in some studies, lifespan. The mechanism seems to be exactly what you'd expect from the mTOR pathway story. When calorie intake is low, the body senses nutrient scarcity and shifts into maintenance mode. Autophagy increases, cell growth slows, repair mechanisms are prioritized, inflammation decreases. The body essentially behaves as though it needs to survive a lean period, and in doing so, it maintains itself more efficiently than it does when energy is abundant. Now, nobody is seriously recommending that everyone reduce their calories by 30% indefinitely. The quality of life implications are significant. Constant hunger is not, for most people, 100% a trade-off they're willing to make for potentially living a bit longer. But the fact that caloric restriction works so consistently across so many species has inspired a lot of research into drugs that might mimic the metabolic effects of caloric restriction without the actual calorie reduction. Caloric restriction mimetics, these are called. Rapamycin is one candidate. Metformin, a diabetes drug that activates an energy-sensing pathway called AMPK, is another. Resveratrol, a compound found in red wine, was for a while considered a candidate, though the evidence for its efficacy in humans has become considerably less convincing over time. The epigenetic clock, measuring how old you really are. One of the most elegant recent developments in longevity science is the discovery of epigenetic clocks, and this one is worth spending a moment on because it's genuinely beautiful. Your DNA, the actual sequence of base pairs that encodes your genetic information, doesn't change much over your lifetime, but the way your genes are expressed, which ones are switched on, which ones are switched off, how loudly different genes are talking at any given time moment, does change. and these changes are controlled largely by epigenetic modifications, chemical tags attached to the DNA, and the proteins around it that function like switches and dimmers. In 2013, a biostatistician named Steve Horvath at UCLA discovered something extraordinary. He found that specific patterns of epigenetic modification, specifically patterns of DNA methylation, where methyl groups attach to DNA at specific locations, change in highly predictable ways with age. So predictable, in fact, that you can look at the methylation pattern of a person's cells and predict with remarkable accuracy how old that person is. This became known as the Horvath clock, one of the earliest biological age clocks, and what it revealed was fascinating. Your biological age, as measured by your epigenetic clock, is not always the same as your chronological age. People who smoke, are obese, or experience chronic stress have biological ages significantly older than their chronological ages. People who exercise regularly, eat well, and manage stress can have biological ages significantly younger. This means that aging is not just a number on your birth certificate. It is a measurable biological state that varies based on how you live. And it means that the goal of anti-aging interventions doesn't have to be just to add years to your calendar. It can be to rewind your epigenetic clock, to move your biological age backward toward younger tissue function. Some research is now showing that this might actually be possible. Partial cellular reprogramming, briefly exposing cells to a cocktail of factors called Yamanaka factors, which are normally used to reset mature cells back to a stem cell-like state, can, in experiments, reverse epigenetic age markers in cells. It's still early, still primarily shown in cell cultures and animal models, but the implication is extraordinary. The epigenetic clock may be reversible. We've spent time with the science, with the biology, with the cutting-edge research labs and the tech billionaires and the molecular pathways. And all of that is genuinely exciting. But tonight, I want to pull back a little, because there's a human dimension to this story that I think deserves some attention. Because for all the sophisticated science we've just explored, there's something interesting in the fact that history has produced a relatively small number of human beings who lived dramatically longer than average. Long before Senolytics existed, long before epigenetic clocks were conceived, long before anybody was thinking about the mTOR pathway. These people, the supercentenarians and the oldest verified humans in recorded history, lived in different countries, different cultures, different centuries. They didn't all follow the same diet. They didn't all exercise the same way. They didn't all have the same socioeconomic status. They didn't agree on much of anything in most cases. And yet, when you look at their lives, certain patterns emerge, certain consistent factors that are, it turns out, remarkably consistent with what modern longevity science is telling us. Jeanne Calment, the longest human life on record. Let's start with Jeanne Calment. She was born in Arles, France, in February 1875. She died in August 1997, at the age of 122 years and 164 days. She is, as of this writing, the oldest human being whose age has been verified by modern documentary standards. She was born before the Eiffel Tower was built. She was a young woman when the first automobiles began appearing on the streets of France. She was alive for both world wars. She lived through the Great Depression, through the moon landing, through the fall of the Berlin Wall, through the rise of the internet. She died 4 months before she would have turned 123. When asked for the secret to her extraordinary longevity, Calment was characteristically direct and slightly impish. She cited a few things. She smoked cigarettes until she was 117, which is typically not recommended as a longevity strategy. and she was almost certainly an anomalous case in this regard. She ate chocolate regularly. She used olive oil both in cooking and on her skin. But what researchers who study her case more carefully tend to emphasize is a different cluster of factors. She was socially connected throughout her life. She had strong social relationships and a sense of community. She was mentally active. She took up fencing at 85 and was riding a bicycle until she was 100. She maintained what she described as a general attitude of equanimity. She was not, by most accounts, a worrier. She took things as they came. "I've only had one wrinkle," she supposedly said once, "and I'm sitting on it." The blue zones, where people just live longer. The concept of blue zones was developed by Dan Buettner, a journalist who wrote a book about the 5 blue zones by researcher and writer Dan Buettner, who worked with National Geographic and a team of demographers and scientists to identify the regions of the world with the highest concentrations of people living to 100 or beyond. They found 5: Okinawa, Japan; Sardinia, Italy; Nicoya, Costa Rica; Ikaria, Greece; Loma Linda, California, USA. These places are geographically dispersed. They have different climates, different cuisines, different cultures, different healthcare systems, and yet they share a remarkably consistent set of lifestyle characteristics that seem to correlate with their exceptional longevity rates. The blue zone lifestyle factors identified by Buettner and his team include natural movement built into daily life, rather than structured exercise; purpose, a reason to get up in the morning, what the Okinawans call ikigai, and the Nicoyans call plan de vida; stress reduction through regular practices like prayer, napping, or social gatherings; moderate, primarily plant-based diet; moderate alcohol consumption, particularly wine, in social settings; and, perhaps most importantly, strong social bonds and a sense of belonging to a community. The people living in blue zones aren't doing extreme things. They're not following complicated supplement regimens. They're not running marathons. They're living in communities where being socially connected, moving regularly, eating mostly plants, and having a sense of purpose are just normal, built into the structure of daily life. And the longevity results are remarkable. Social connection, the most underrated longevity factor. If there's one thing that consistently comes up in the research on what makes people live longer, it's something that doesn't fit neatly into a pill or a protocol. It's other people. Social isolation and loneliness are, according to a growing body of research, among the most significant risk factors for early death. A major meta-analysis published in 2015 found that social isolation increased the risk of early death by approximately 29%, while loneliness increased it by 26%. These are effects comparable in magnitude to smoking 15 cigarettes a day, comparable to clinical obesity. This is not a soft finding. This is robust epidemiology. Being alone, consistently, chronically, without meaningful social connection, is bad for your biology in measurable, significant ways. It increases inflammatory markers in the blood. It disrupts sleep. It elevates cortisol levels, the stress hormone. Chronically, it affects the immune system. It is, in a very real biological sense, harmful to the body. Why would evolution have designed us this way? The answer, as with so much about human biology, goes back to the ancestral environment. For our ancestors on the savannah, social isolation was genuinely dangerous. Alone, you couldn't hunt effectively, couldn't defend yourself, couldn't care for children. The social group was the survival unit. Being cut off from it was literally a threat to life. So evolution built social isolation into the body's stress response system. Loneliness triggers biological threat responses, elevated cortisol, increased inflammation. In the same way that physical danger does, the body treats being alone as an emergency, because for most of human evolutionary history, it was. The modern world has created conditions: urban isolation, digital connection without physical presence, declining community structures, that are deeply at odds with this ancient biological wiring. And it may be contributing, in quiet and underappreciated ways, to the rates of chronic disease and shortened healthy lifespan that we see in contemporary society. Sleep. The most important thing you're probably not doing enough of. Another factor that comes up consistently in both Blue Zone 1 and 2 is the importance of social support research. And modern longevity, science is sleep. For most of human history, the importance of sleep was understood intuitively. People slept when it was dark, woke when it was light, and didn't give the matter much more thought. It was only in the modern industrial era, with artificial lighting and 24-hour schedules, and the cultural glorification of busyness and sleeplessness, that sleep started being treated as something optional, something to minimize, something that serious, productive people powered through. This turns out to be a very significant mistake. The science of sleep and aging has exploded in the 21st century, past 2 decades. We now understand that sleep is not passive rest. It is an intensely active biological process during which the brain performs crucial maintenance that cannot be done any other way. Most notably, during deep sleep, the brain's glymphatic system, a waste clearance system that runs through the spaces around brain cells, is highly active, flushing out metabolic waste products that accumulate during waking hours. Among the waste products cleared by the glymphatic system during sleep are amyloid beta and tau proteins, the same proteins whose accumulation in the brain is associated with Alzheimer's disease and other forms of age-related cognitive decline. When you consistently don't sleep enough, these proteins accumulate faster. Over time, this accumulation contributes to the very cognitive deterioration that most people think of as an inevitable feature of old age. It is not inevitable. It is accelerated by sleep deprivation. The recommended amount of sleep for adults, 7 to 9 hours per night, is not arbitrary. It is calibrated to the time the body needs to perform this maintenance. And consistently getting less than 7 hours per night is associated, in large-scale epidemiological studies, with significantly increased risk of cardiovascular disease, metabolic disorders, immune dysfunction, and accelerated biological aging as measured by epigenetic age clocks. Stress, the invisible accelerant. And then there's stress. Chronic stress is, in a very real biological sense, one of the most potent accelerants of aging we know of. The stress response, the fight or flight system, driven by cortisol and adrenaline, is brilliantly designed for short-term threats. A predator appears. Your heart rate spikes. Your senses sharpen. Glucose floods into your muscles. Non-essential functions shut down temporarily. You fight, or you run. The threat passes. The stress response turns off. Your body recovers. This is fine. This is adaptive. This is what the system was designed for. What the system was not designed for is being activated continuously for months or years at a time in response to modern threats, financial stress, relationship stress, work pressure, social anxiety, the low-grade persistent stress of navigating a complex, demanding modern world. Chronic stress keeps cortisol levels chronically elevated, and chronically elevated cortisol is deeply damaging to almost every system in the body. It suppresses the immune system. It increases inflammation. It disrupts hormonal balance. It accelerates telomere shortening. This was directly demonstrated by a landmark study by Elixir and colleagues, which showed that women experiencing chronic stress had significantly shorter telomeres than age-matched low-stress controls. The difference was equivalent to approximately 10 years of additional aging. Stress doesn't just feel bad, it physically accelerates the biological processes of aging, measurably at the cellular level. This is why stress management practices, meditation, mindfulness, prayer, social connection, regular rest, time in nature, are not just wellness trends or lifestyle preferences. They are, from a longevity science perspective, genuinely significant biological interventions, practices that reduce chronic stress levels, reduce chronic cortisol, reduce inflammation, protect telomeres, and slow measurable biological aging. The people living in blue zones aren't just eating differently or moving more. They are, by design of their communities and cultures, experiencing dramatically less chronic stress than most people in modern developed societies. And that matters enormously. We're getting toward the end of our journey tonight, and I want to spend this final section, before we close things out, looking forward, because everything we've discussed so far has been leading to this question. Can we actually stop aging? Not slow it a little, not add a few extra healthy years, but genuinely, fundamentally, eliminate the biological process of aging as a cause of human death? This is the longevity escape velocity question. It's a term coined by Aubrey de Grey, a British biogerontologist who has been one of the most vocal advocates of the idea that aging is in principle a fully solvable engineering problem. The concept of longevity escape velocity is this: at some point, 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 at some point. The rate at which science is extending human lifespan will exceed the rate at which any individual is aging. In other words, For every year you live past that point, science will have added more than a year to your remaining life expectancy. You will be, as long as you keep living and keep benefiting from ongoing advances, effectively outrunning aging indefinitely. De Grey has long believed that we are closer to reaching this threshold than most people realize. His organization, the Sense Research Foundation, has been working for 2 decades on identifying and addressing the specific types of biological damage that accumulate with age, on the theory that if all of those damage types can be periodically repaired, like maintaining an old car by replacing parts as they wear out, the body could, in principle, be maintained indefinitely. Most mainstream biogerontologists consider de Grey's timeline optimistic. Some consider it far too optimistic. But the underlying idea, that aging is a biological damage process that is, in principle, subject to engineering solutions, is increasingly taken seriously as a scientific proposition, even by researchers who are skeptical of the more extreme longevity claims. Gene therapy and the future of aging. One of the most dramatic potential avenues for anti-aging medicine is gene therapy, the ability to alter the actual genetic instructions in living cells, to switch genes on and off, to correct mutations, to add new genetic information, is a technology that has been developing for decades and has recently reached a point where its clinical applications are genuinely expanding. In the context of aging, gene therapy for longevity could mean several things. It could mean correcting specific age-related genetic mutations in somatic cells, the non-reproductive cells of the body. It could mean activating genes that promote cellular maintenance and repair. It could mean suppressing genes that drive aging-related processes. The experiments being done in animal models are striking. In 2021, researchers at Harvard Medical School, including the prominent geneticist David Sinclair, demonstrated that epigenetic reprogramming using Yamanaka factors could reverse signs of aging in the eyes of mice, restoring vision in aged mice with optic nerve damage. The treated mice showed measurable improvements not just in their eye function, but in the epigenetic age markers of the cells in their eyes. Sinclair's own research has been among the most ambitious in the field. His lab has published work arguing that epigenetic information loss, the gradual deterioration of the chemical tags that control gene expression, is a central cause of aging, and that this deterioration can, at least in cellular and animal models, be reversed through targeted epigenetic reprogramming. If this holds up in humans, and human trials are beginning, the implications are extraordinary. Not just slowing aging, not just adding healthy years, but potentially reversing biological age in specific tissues, CRISPR, and the editing of aging itself. Then there is CRISPR-Cas9, the gene editing technology that won the Nobel Prize in Chemistry in 2020 for its developers Jennifer Doudna and Emmanuel Charpentier. CRISPR allows scientists to edit DNA with unprecedented precision, cutting out specific sequences, inserting new ones, correcting mutations at targeted locations in the genome. In the context of aging, CRISPR gene editing opens up possibilities that would have seemed like pure science fiction 10 years ago. Could you edit the human genome to reduce the expression of pro-aging genes, to increase the activity of tumor suppressor pathways, to extend telomeres, to make human cells more resistant to senescence? The honest answer is, in principle, possibly yes. In practice, we're not there yet. The complexity of the aging process, the 9 hallmarks, the multiple interacting pathways, the fact that many pro-aging mechanisms are also protective in other contexts, means that this is not a simple problem of flipping a few switches. It will require an enormously sophisticated understanding of which switches to flip, in which direction, in which cells, at which times. But the technology exists. The question is now one of knowledge. understanding the aging process well enough to know where to precisely intervene, rather than capability, AI, and the acceleration of aging research. And here, at the intersection of aging science and technology, is where things get genuinely extraordinary. Because artificial intelligence is beginning to transform the pace of longevity research in ways that are difficult to fully appreciate. AI in drug discovery has already demonstrated that machine learning can be used to predict the activity of new compounds. Systems can identify promising drug candidates for various diseases orders of magnitude faster than traditional methods. In aging research specifically, AI is being used to analyze vast genomic and epigenomic data sets, identify patterns invisible to human researchers, model how different interventions might affect the complex interacting pathways of aging, and accelerate the identification of potential therapeutic targets. AlphaFold, the AI system developed by DeepMind that has essentially solved the protein structure prediction problem, a challenge that had stumped biochemists for 50 years, is directly relevant to aging research, because understanding the three-dimensional structure of proteins is fundamental to understanding how they function and how they can be targeted by drugs. Protein misfolding and aggregation is one of the hallmarks of aging. AlphaFold's capabilities are already accelerating the design of potential interventions. The combination of advanced molecular biology, CRISPR gene editing, epigenetic reprogramming, and AI-accelerated research is creating a situation where the pace of progress in longevity science is compounding rapidly. Things that were purely theoretical 10 years ago are now in early clinical trials. Things that are in early clinical trials today may be standard medical practice in 20 years. The philosophical question: should we live forever? But here's where I want to pause for just a moment, because all of this extraordinary science raises a question that the science itself can't answer. Should we live forever? Is radical life extension, centuries, or indefinite lifespans actually a good idea? Is it something that individuals should pursue? Something that society should facilitate? Something that the human species should want? This is a question that philosophers, ethicists, theologians, and just regular people have been wrestling with since at least the days of Gilgamesh. And it doesn't have a simple answer. There are arguments in favor, and they're compelling. Aging causes enormous suffering. Age-related diseases, heart disease, cancer, Alzheimer's, stroke, are the leading causes of death in the developed world, responsible for the vast majority of human suffering and medical expense. Defeating aging would eliminate most of this. It would mean more time with the people we love, more time to create, to learn, to experience the accumulated wisdom of people who live centuries rather than decades. But there are genuine concerns too. Overpopulation and resource strain in a world where people stop dying of old age. The difficulty of social change in a world where old power structures never yield to new generations. The psychological challenge of living indefinitely, the potential for meaninglessness in a life that goes on forever, when the scarcity of time is part of what gives each day its weight. There's no settled answer to these questions. They're among the most important philosophical questions our species will face in the coming century. And the fact that they are now practical questions, not just abstract philosophical thought experiments, is itself remarkable. We are possibly the first generation in human history that will see at least the beginning of a genuine scientific answer to the oldest question human beings have ever asked. Why do we age? And what can we do about it? What you can do right now. Before we close, though, let's come back down to earth for a moment, because not all of us have access to cutting-edge longevity clinics or experimental drugs or billionaire-funded research institutes. But the good news is that the most powerful longevity interventions available right now are largely free, or cheap, or at least within reach of most people. Sleep, 7 to 9 hours a night, not as a luxury, as a biological necessity. Your glymphatic system needs that time to clean your brain. Your cells need that time to repair. Your body is doing maintenance that cannot be deferred. Move regularly. Not marathon-level exercise, regular moderate movement. Walking, cycling, swimming. The kind of movement that blue zone populations have naturally built into their lives without even thinking of it as exercise. Eat mostly plants, not necessarily exclusively, but a diet centered on vegetables, legumes, whole grains, and fruits, with limited processed foods and moderate animal products, consistently shows up in longevity research as associated with better health outcomes and longer healthy life. Maintain your social connections. Prioritize them. Real ones, not just digital ones. The evidence that strong social relationships extend life is among the most robust in all of epidemiology. Manage your stress. Not because stress is uncomfortable, though it is, but because chronic stress is directly, measurably, aging your cells. Meditation, time in nature, regular rest, whatever works for you. None of these are new ideas. In fact, most of them are old ideas. They show up in Galen, in Hippocrates, in traditional Chinese medicine, in the blue zones, in the modern research. The wisdom has been there for a long time. The science has just spent the last 2,000 years slowly building the tools to explain why it's true. And that, I think, is where we drift to a close tonight. We started with a jellyfish that doesn't die. We traveled through the cells of your body and the arithmetic of evolution. We spent time with 500-year-old sharks and 30-year-old naked mole rats, and a 190-year-old tortoise on a tiny Atlantic island, who has outlived everyone who was ever born in the same year as him. Twice, we walked through ancient Egypt and ancient Greece and ancient China. We met alchemists chasing elixirs and Victorian scientists building the first real theories. We visited the molecular biology revolution and the tech billionaires betting billions on cheating death. We met Jeanne Calment, smoking at 117, sitting on her only wrinkle, and underneath all of it, through all the history, all the science, all the mythology and philosophy, there was one simple question. Why do we age? Why does the smartest animal on Earth also happen to be so temporary? And the answer, as best we currently understand it, is this. Because for most of our evolutionary history, we have been living in a world where the majority of our food was not available to us. History, being temporary, was the most efficient strategy. Because reproduction mattered more than maintenance. Because the deal evolution made on our behalf. More children, faster, even at the cost of a shorter, deteriorating body, was the winning deal for most of our species' history. But the world has changed. We have changed. We have the knowledge now to begin questioning that deal, to understand it, and maybe, in the not-too-distant future, to renegotiate it. That is, if nothing else, one of the most remarkable things about being human right now. That we are the first generation in all of human history where this question is moving, slowly, carefully, but genuinely, from philosophy to science, from why to what if, to perhaps someday, how. Tonight's journey was a long one, and if you made it all the way here, you're in for a treat. If you drifted through all of history, all the science, all those beautiful, strange animals, I really hope something tonight stayed with you. If it did, and if you feel like it, maybe leave a like on this video. It genuinely helps more people find their way to these stories. And if you want more long, gentle journeys through history and science with me, come join us at Historian Museum. I'll have another story waiting for you whenever you're ready to settle in. Good night, everyone. Sleep well, and remember, somewhere out there, a 500-year-old shark is quietly cruising through the dark water, unbothered by time. Maybe there's a lesson in that.